Okay, so today we're going to talk about solving exponential equations. Um, think I actually am here for part of this lesson, so you may not need uh, this entire thing, so feel free to skip through. I will be here on Thursday because we have a home game. So I'll be there to teach both classes. So only the Tuesday this week I'll be away. And there's just this one fill in the blank in this paragraph. So last year we learned to solve exponential equations in the 3U course by writing our equations with a common base is the blank. And once we've done that, we can set our exponents equal to one another. And of course, this is still a viable method when the numbers work out nicely. So we're going to look at a couple examples here where that does work out nicely and then talk about how do we solve those problems in the past and how can we solve them with what we've learned in the last little bit. So the first question here, when is 4 to the x equal to 256? So we can use that example of a common base. Well, 256, that's the same as 4 times itself 4 times. So 4 times 4 times 4 times 4. Now they have the same base. 4 to the power of x equals 4 to the power of 4. And just as we said in the sentence above, so once they have the same common base, we just set the exponents equal to each other. So in this case, yeah, x equals 4. And so just find that common base. Your exponents have to be equal to one another. So look at two more examples here. The second question here, 25 to the power of 2 minus x equals 125 to the power of 1 minus x. There's no easy way to write the bigger number 125 as 25 to the power of something. Not that it's impossible, but it's maybe not obvious. But instead, because they're both powers of 5, we can rewrite 25 as 5 squared and 125 as 5 cubed. So we have 5 squared to the power of the same exponent as before, 5 cubed to the power of the same exponent as before. And using our exponent laws, we can multiply those exponents together. So 2 times 2 minus x, we get 4 minus 2x. 3 times 1 minus x, we get 3 minus 3x. And now we have the same base with two different exponents. So we just set those exponents equal to one another. It's the only way they can be equal. And now it's just a linear equation. So we move our x's to one side and our non-x's, our constants, to the other side. So add 3x and we get x. Subtract 4 and we get negative 1. So x has to be equal to negative 1. Don't believe me? Sub into your equations here. So negative 1, we would get 2 minus negative 1 is positive 1. Or sorry, no, that's not correct at all. 2 minus negative 1 is 3. So 25 cubed. And we get 125 squared. So 25 cubed, 125 squared. We could check those on a calculator, but those are equal to one another. The very last one, same thing. Try to get the same base. So the 1 over 9, well, we talked about negative exponents. 1 over 9 is the same as 3 to the power of negative 2. And so then we have that same exponent of x minus 10. Multiply the exponents here together because you have a power to an exponent. Negative 2x plus 20. Don't forget negative times negative, you get a positive. And now your exponents have to be equal to one another. And we can add 2x to both sides and subtract 2 from both sides. We get 6x equals 18, which tells us x should equal 3. Can always double check, put it in a calculator. So 3 to the power of 14 may or may not work nicely in a calculator. And 1 over 9 to the power of negative 7. Those should give us the same answer. Last year in the 3U course, at least how I've taught it in the past, if we had something like this, you would have had to sit there with trial and error and try to figure out like what exponent can I put on 3 to get 19. And so we know it's somewhere between 2 and 3 because 3 to the power of 2 gives you 9. 3 to the power of 3 gives you 27. it's roughly in between 2 and 3. But now that we've talked about logs, we can just rearrange this into its logarithmic form. So log base 3 of 19 equals x. And we've talked about how to put that left side into a calculator. So the instructions for this example 2 on your notes say we're going to round answers to 3 decimal places. So we can write in log of 19 divided by log of 3 on our calculator. Always the argument of the log on the top and the base of the log on the bottom. When you're changing the base, using our change of base from one of those first 2 days, and then if we sub that in, you get it's equal to approximately 2.680, and I included the 0 at the end because that was rounded as well. So that shows me not just it was rounded to 2 decimal places, but it was rounded to 3 decimal places. Got one more example here for example 2. Second example here, 20 times 5 to the x plus 1 equals 400. Well, I can divide both sides by 20 to get rid of that 20 that was on the left, and we'll get 5 to the x plus 1 equals 20. Then we can convert things into our logarithmic form. So log base 5 of 20 equals that exponent equals x plus 1. Subtract 1 from both sides, and log base 5 of 20 is something we can put in our calculator. If you need to, log 20 over log 5, and then subtract 1 at the end, and we should get approximately 0.861. Back to solving here, so no decimal places asked for. Like the last few, 36 to the 2x minus 1 equals 216 root 6. May not be overly obvious depending on your comfort level, but 36 is definitely a power of 6, and we have another 6 here, so maybe we can check, yeah, it's 216, and yeah, it turns out, well, 216 is the same as 6 cubed, so I can replace that with 6 cubed, my root 6, so I can use my fractional exponents, that's the same as 6 to the power of a half, and 36 is the same as 6 squared. And so then using fraction rules to combine things, I multiply my exponents on the left, and I get 4x minus 2 in my exponent. And then here I got to add, so 3 plus a half, I get 3.5, or 7 over 2. Make your exponents equal to one another. And then, well, you can get rid of the fraction, just multiply everything by 2. You don't have to worry about the fraction anymore. 8x minus 4 equals 7. Add 4 to the right. We get 11. And then divide both sides by 8. So all of that, I know I ripped through that pretty quick. Let me know if any questions at all, but x should equal 11 over 8. And so then on the back of your note, I've thrown on 2 examples that I generally see people have some trouble with. So in this first example, the very first thing I'm going to do is I'm going to split the left terms, this 2x plus 2. I'm going to use my my product rule for powers. And I'm going to split that into a 2x times a 2 squared. So we're used to kind of doing the opposite. Here I would have to add these powers, and I could turn it into something like this. I'm just reversing it. I'm doing the opposite. So I've split it into its 2 separate powers. And what that's going to allow me to do now is I have a common factor. So in this first set, I have a 2 to the power of x. In this second part, I have a 2 to the power of x. So I'm going to take out a common factor of 2 to the power of x. And what do I get left with? Well, I have a 2 squared from, I have a 2 squared from here. And then, well, this was just negative 2 to the x, so I would get a factor of negative 1 there. And if that looks strange, try multiplying that back out. Distribute your brackets. But 2 squared minus 1, I get 3. 4 minus 1, I get 3. Divide both sides by 3. And from there, it's quite a simple question. 8 is the same as 2 cubed. So x has to equal 3. But yes, this splitting things apart and then the factoring is where some people can get messed up. But yes, if you think of it, this 2 to the x is multiplied by 2 squared, and this 2 to the x is multiplied by -1. That matches what we have in the step above. Don't forget, when you're factoring something out entirely, you still get left with that factor of 1 or -1, depending on the sign. So one more question here right at the end. Again, please let me know if you have any questions. Don't wait. Put a star beside it. Remember to ask me if this is something I didn't have time to go through in class, because again, I don't know how long I get to stay necessarily tomorrow. Or I guess today for you listening to it today. But let me know if you have any questions. This one's tricky because 2 to the power of x plus 1 and 3 to the power of x minus 1. 2 and 3, there's no like common factors, or there's no real easy way to write one as the base of another. They're both exponentials, so I can't do what I did up here and just rewrite it as a log and easily calculate things, because I have powers of x on both sides. And so there is a few approaches you can take. The way I'm going to talk through here is take the log of both sides. So the log of the left side should still equal the log of the right side. And what that is going to allow us to do is use our log rules, our power rule for logs, and we can bring that exponent out in front and multiply. So x plus 1 times log of 2 and x minus 1 times log of 3. And now we can use our distributive property and multiply things out. So x plus 1, I'll multiply the x, and I'll multiply the 1 by log of 2. Same with the x minus 1 on the right side. And so I get 4 terms. And so it doesn't really look like I'm helping simplify things. I'm making things more complicated. What that's going to help with is we can move all of our terms, just like in grade 9 linear equations, all our terms with x to one side and all our terms without x to the other side. So that negative log 3 I bring over, it becomes positive log 3. The x log 2 becomes a negative log 2 on the right side. And so now all the x's are on the right. All the things that don't have x are on the left. I think here I've combined the two logs on the left just because you can, I suppose. So log 2 plus log 3. Well, adding logs together is the same as multiplying your arguments. So that's the same as log 6. And on the right, I have a common factor of x that I can take out. And so I get log 3 and a negative log 2 left in the brackets. And I think I've written it the same way here. So this is a subtraction. I can use that as a division. Log base 3 over 2. And because I've written it like that, when I do my division to get rid of the part that's multiplied by x, I divide by log 3 over 2. And this is a change of base. Sometimes questions, especially in a non-calculator section, sometimes a question will ask you, can you write this as a single logarithm? Well, I can right here. Just like when we try to calculate something like this in our calculator, you do the log of the argument over the log of the base. I can work my way backwards. Now that's not what this question asked. And if you look at the solutions I post online, I didn't combine these things. I didn't combine these things. I just left it all separate, and you can just plug that into your calculator. Or if you do the combined form, either way, you should get 4.419 as your answer for this one. So again, a little funkier. Let me know if there's questions at all, or if maybe you feel like I didn't do a good job explaining in this video. And tomorrow, we're going to start to look at some log equations, and again, trying to find x. So solving for our variable. So anytime you see the word solve, gotta find what your variable equals to. That is the end of this lesson. It's not super long, but a couple new tricks. Let me know if you have any questions. And I will be in at lunch tomorrow, Wednesday this week. If you have questions on test, notes, otherwise, let me know.